All right, I think we will start. I guess the first thing, thank you everyone for coming this early in the morning. I know it's 9 o'clock, it's a bit of a struggle. At least personally for me, that's always been the case. It's like after my friend Army Day. So I guess today is 14th of June. So I want to start by taking a stroll in memory lane and go back to what happened in 2014, just a few years earlier, because some pretty momentous things happened. For example, did you know that Taco Bell finally announced their breakfast menu back in 2014? I didn't know that. And then Alibaba had the biggest IPO ever, $25 billion, which, being a Chinese company and all, is a bit of a national pride for me. And then you also have the Grumpy Cat, and of course, everyone was singing Let It Go on the tubes and in the bars and everywhere because of Frozen. And of course, Amazon announced the AWS Lambda at the reInvent that year as well. And since then, we've had this whole serverless thing that's been bubbling under and getting more and more momentum every year. And I've also been able to play this really wonderful game whereby every time I say the word serverless, someone reminds me that there's still servers somewhere, which of course is missing the point entirely, because serverless is serverless for the same reason that Wi-Fi is wireless, even though there's still wires connected somewhere. But when you're trying to connect to the NDC Wi-Fi, for example, those wires are not your concern anymore. So I think as the industry, as a community, we've argued for quite a while, what does it actually mean to be serverless? And eventually we settled on 3 things. Serverless is any technology that you don't pay for it when you're not using it, and you don't have to worry about scaling, you don't have to worry about provisioning and managing servers. You may have also heard the term function as a service, or FaaS, which is very closely related to serverless. And that's where you're going to find AWS Lambda and Azure Functions or Google Cloud Functions and so on. And it's a pretty accurate description for the technology because it's very close to what you actually do in terms of writing a function, a handler function that allows the platform to call on your behalf when some event happens in the ecosystem. It could be someone making an HTTP request to an endpoint, or someone publishing a message into SNS or Kinesis, and so on. And when you compare functions as a service to infrastructure as a service to containers as a service or platforms as a service, you can see that it's very close to platform as a service in terms of what does the provider handle for us versus what do we have to manage ourselves. The main difference being whether or not the unit of scaling is the application or the individual functions that make up your application. And just because something is fast doesn't necessarily mean that it's serverless and vice versa. Take Kubernetes, for example, which allows you to run fast on your own Kubernetes cluster. By our definition of serverless, you shouldn't have to pay for it when no one's using it. But even when no one's running functions on that Kubernetes cluster, you still have to pay for that cluster yourself. And of course, you still have to think about scaling and provisioning and managing servers that runs your Kubernetes cluster. Equally, when you have services like S3 or Google BigQuery or Azure Blob Storage, so table storage, for example, those are services that you don't have to think about scaling. You don't have to think about managing servers, and they just auto-scales. So by our definition, they are also serverless, even though they are not functions as a service. A lot of the industry leaders, take Simon Wardley, for example, who's known for his mapping technique. They believe that serverless will fundamentally change how we build and run software in the future, and for good reason too. For starters, your application tend to be a lot more scalable. Sure, there's still going to be some scaling limits. Most of them are soft limits. For example, Amazon limits you to scaling up to 500 containers per minute for both your protection as well as for theirs. But that is still a lot faster than most of us is able to do with our own, say, Kubernetes cluster. Because to reach that kind of scaling speed, you have to have a lot of spare capacity just lying around. And you have to pay for those capacity. You have to pay for those capacity even when you're not using it. So for you, in terms of the cost perspective, it's really not efficient. But as a provider, they have the scale economy. So for them, it's perfectly fine to have a lot of spare capacity lying around so that their customers can tap into even when they need it. And then there's the whole aspect of you don't pay for it when you're not using it. So chances are your system can also be a lot cheaper to run as well. And you also get multi-AZ out of the box. So you get a good baseline resilience out of the box without having you have to do anything yourself. But for me, the biggest reason to go to serverless is the fact that from having an idea to having something running in production so that you can start testing the idea against the market, there are so many things we have to do just to get there. We have to decide what language and what framework we want to use. We have to learn those frameworks, and we have to think about configuring the servers. We have to decide how we're going to do deployment, CI/CD, and we have to build up those machine images and do capacity planning meetings and so on and so forth. But when you do serverless, a lot of that becomes either irrelevant or they have been drastically simplified. Of course, you still have to think about deployment, for example, but with a lot of the built-in capabilities as well as tools like the serverless framework, deployment becomes so simple. And you don't have to think about configuring load balancers and auto-scalers anymore. A lot of that just comes out of the box. So in return, you get far greater velocity to production. And you do that by minimizing the amount of undifferentiated heavy lifting that you have to do yourself, including configuring servers and configuring AMIs and so on, and setting up the servers and so on and so forth. And you also give yourself less operational responsibility that you have to do yourself by offloading more and more of them to the provider that you're working with. Of course, ultimately, ops is still a responsibility you have to bear on your customer's behalf. And with serverless, you still have to do a lot of things. You still have to figure out how you're going to do CI/CD and the logging, monitoring, distributed tracing, and so on. I did a separate talk last year at the CodeMotion Milan, where I talked about a lot of these things in terms of how do you test your function locally, how to make sure you do continuous delivery, and all the monitoring, operational side of things. So go check it out afterwards. So I worked with a piece of a non-trivial serverless application when I migrated a social network to run pretty much entirely on serverless. And one of the things I learned there is that event-driven architectures has more and more become the norm in the serverless world, and events are a great way for you to build systems in a really loosely coupled way. And functions as service offerings such as Lambda is the perfect glue or connective tissue that allows you to connect all these different services together. And over time, you see people use the Lambda with other event sources in a similar way over and over, and certain patterns start to emerge. And as should be customary for any talk that touches on design patterns, I'm going to start with a warning that a design pattern is not necessarily a recipe for success, nor is it a recipe for disaster. It's just what it is, that a repeated way that something has been done up to now. And it's no real substitute for really trying to understand the problem that you're dealing with, as well as the constraints that you're working with. And if you're just blindly following patterns, you're not aware of how it fits your context, then you also run the risk of miss the point that when the context underneath that underpins those design patterns and best practices, as they shift around, today's best practices and design patterns can become tomorrow's anti-patterns. So I guess what I'm saying here is that I'm not here to sell you some magic bullet that you can just blindly follow, because magic bullet doesn't exist, and we should stop trying to follow them, trying to find them all together. Is the mic still on? Okay, I'm going to keep talking anyway. So all I'm doing here is I'm going to show you a few patterns that I've noticed as I talk to many people that are using serverless. And my name is Yan. I'm a principal engineer for a company called The Zone, based in the UK. We are a subscription-based platform for watching sports, and we often go by the tagline of Netflix for sports, because it's a very similar model in terms of being a subscription-based platform. We have lots of different sports and leagues available on our platform already, and we are always adding more and more different sports onto the platform, and we're spending a lot of money doing so as well. We just recently announced a $1 billion deal to bring boxing to the platform. And some of the monies that are involved with sports image rights is just mind-blowing. Our platform is available in 5 countries right now, but we're expanding that pretty aggressively too, and it's available across more than 30 different platforms, including smartphones, Apple TV, as well as some really old set-top boxes available in Japan. And any moment in time, we have about 500,000 people watching sports on our platform. So it does come with quite a lot of interesting technical challenges as well. And if you're interested in solving that kind of challenges, we're also hiring in multiple locations. Go to engineeringthezone.com to find out, or you can follow us on Twitter to see what the team has been up to. Personally, I've been using AWS for almost 10 years now. And as I mentioned earlier, I also worked on some non-trivial serverless applications. And some of my work has been also captured in the well-architected white paper that Amazon published last year. I want to start with a very simple pattern where I see a lot of people now are moving cron jobs that they run on their server onto the cloud using a combination of CloudWatch events, which allows, and the Lambda. And with CloudWatch events, you can, I think there's something, I'm pretty sure there's something very similar in the Azure as well, where you can say, hey, I will have something that I want to run every, say, 5 minutes. And when that happens, trigger a Lambda function to do something. And from that, you can also go a lot further as well. You can use that to automate a lot of the operational things that you tend to do in your environment. For example, whenever you write something to send it out from your Lambda function, that gets captured and shipped into CloudWatch logs automatically for you. But CloudWatch logs is not great for searching. So what people tend to do is they go to the console and say, I want to stream this log, CloudWatch log group to a Lambda function, and from there, I'm going to ship all of my logs to some log aggregation service that I'm using, which could be a self-hosted elk stack, for example. But you don't want to create this manual process in your development cycle where you have to always remember to go to the console and subscribe your new log group to a Lambda function and so on. So what you can do is automate this by enabling CloudTrail in your environment, which then opens the door for you to create event patterns against API calls that happens in the ecosystem on your behalf. So whenever the Lambda service creates a new log group with the create log group API call, you can tap into that and react to it with a Lambda function whose job is to then subscribe that new log group to your log shipping function. So now, whenever you create a new function, you create a new log group, you will automatically get the capability to ship those logs to your log aggregation service. And this pattern of using CloudTrail events, events that are captured in CloudTrail to then create event patterns and trigger Lambda function, that is actually a reusable pattern. For example, something you also have to know about CloudWatch logs is that by default, it retains your logs forever. And if you're going to be shipping your logs to somewhere else already, it really doesn't make sense for you to pay, 3 cents per gigabyte per month going on forever. So one of the things you could do is use the same technique and just have a Lambda function to then automatically update the retention policy to something more reasonable, maybe 7 days. And whenever you create a new API, maybe you also have a convention in the team to also want to create alarms around the latency, say the 95th percentile latency for individual endpoints so that they shouldn't go beyond, say, 2 seconds. You can also automate that so that whenever you create a new API, you can tap into the create deployment API call that the system makes for you and then automatically create those alarms and those dashboards. You can also do things around things that happen in the console. For example, when you see someone logging into the AWS console at some weird time or from a weird location that you don't have any people, then you could also create the Lambda functions to react to that and automatically alert someone that maybe someone's credentials been compromised and we have someone logging into the console and so on and so forth. Of course, a lot of us build web applications for a living, and you can also do that with Lambda and serverless very easily. You may have a single-page application that's put inside, that's deployed into S3 and exposed through CloudFront so that you get CDN. And on the back end of things, you have a Lambda function behind API gateway, and it's using DynamoDB tables as the backend database. For authentications, you can also use serverless offerings such as Amazon's Cognito service, which out of the box supports a number of user flows in terms of the registration, sign in, sign out, change passwords, and so on. And you get a number of the good practices out of the box as well in terms of how you manage passwords securely, and also supports things like MFAs and capture and so on. You can, for example, building a mobile app, you can use some other third-party OAuth provider, and you can authenticate against those OAuth provider, and the JWT token you get back, you can then send it to Cognito Federated Identity Service, which would then, in that case, would validate the token on your behalf. And if the token is valid, and you can exchange that token with to a temporary AWS credential, so that allows the mobile app to directly access resources that you have in AWS. So, for example, if you want to use the IoT service that AWS provides, this is how you would do authentication against the IoT service. And if you are publishing events from the mobile app, rather than having to create a service just so that you can provide some authentication layer in between, you can just have the mobile app talk directly with Kinesis and publish client-side events that way as well. And oftentimes, you also want to do multi-region for better resilience, but also sometimes for better latency for your users as well. And nowadays, it's become really easy to build a multi-region active APIs on AWS, because DynamoDB now supports global tables, where you can have a table replicated across multiple regions for you automatically. And API Gateway also supports regional endpoints, so you can bring your own CloudFront distribution in front of API Gateway now as well. And to set up a multi-region setup with API Gateway and Lambda and DynamoDB behind the scenes is really, really easy. And my friend Alex Casaboni, now working for AWS, has also did a webinar session recently as well to show you exactly how you can do that setup. So go check it out afterwards. Another thing you see people do a lot with Lambda is building data processing pipelines. And of course, on AWS, the de facto solution for data lake is S3, where you can put all of your events data into it, and you can manage your access with IAM permissions, and you can also encrypt data using KMS. And this all comes out of the box. And Amazon also announced a new service at the last re:Invent called Macy, which uses a machine learning to then try to understand the data you have in the S3 in case, and try to alert you whenever it detects that you have potentially user identifiable information in the S3 bucket, which nowadays with GDPR in full effect is also really going to be really important for us now, and also can alert you when you see something that looks like secrets or credentials or API keys, and you can create and can alert you automatically. In terms of getting data into S3, what you also find is that a lot of people will be using something like Kinesis and Kinesis streams and connect that to Kinesis Firehose and pipe all the data and batch them and save them into S3, or without you having to write any code yourself. It's just a field configuration, and you can also automate that using CloudFormation or using Terraform as well. And of course, when you have events going to Kinesis, you can also have Lambda functions that react to them and do some other processing. And even when you have Firehose, you can also do some additional manipulation and the transformation using Lambda functions as well. And once the file has been dropped into S3 bucket, you can also react to that, because that is also an event source for Lambda to then do other processing. Perhaps you want to take whatever data has been saved into S3 and put them into Elasticsearch so that you can index those documents. Or maybe you want to record some metadata in the DynamoDB. Or in my particular case, I've been using Google BigQuery for many, many years, which is a really fantastic platform for doing BI workload. You can also have Lambda functions stream any data you have stored in S3 directly into Google BigQuery as well. And of course, Amazon also announced the counter offering to BigQuery called Athena. So nowadays, as you save all of your data into S3, you can also analyze them you can also run ad hoc queries against them using Athena, and you can visualize the results using Amazon's QuickSight service as well. So all in all, nowadays you can build an entire data processing pipeline almost without having to write any code yourself. And I touched on this event-driven aspect of serverless at the start, and I want to just drill into it a little bit more. So of course, with event processing, there's a lot of patterns you may have heard about in terms of event sourcing or just or unified log processing, for example. I'm not going to talk about any of those specific patterns. This is more of, I guess, a trend in the how we build systems, nowadays versus necessarily a design pattern. So Kinesis, we talked about that earlier already. This is where you typically would use in AWS to stream a lot of things, all the events that's happening in your system into a stream. And when you have microservices, you've got different boundary contexts. Those different boundary contexts, you can make state changes inside them. And when something changes, you can also publish that as an event to a Kinesis stream, so that other subsystems can also react to those state changes in the system. And those systems can also have their own backend stores for data, which could be DynamoDB, it could be Kinesis, so it could be SNS, could be S3, it could be something, whatever it is that you use. And of course, as those other subsystems create state changes, they can also then publish events back into Kinesis stream so that other systems that are interested in those kind of state changes can also react to them as well. And using events, you can build a really loosely coupled system that way. And suppose you've got multiple microservices, each one of them wrapped nicely inside their own bounded context, and when something happens in one, you don't want to have a synchronous communication to another service to notify them. Instead, everyone would just be communicating through events by publishing and subscribing to a shared stream. And this is, of course, not a new idea. It's been around for many years, and many people call them unified log processing. As you can probably see from the dates on that, my friend Alex Dean has been trying to write his book since about 2014. So this book has been a work in progress for quite a number of years. And one of the things that you run into, one of the challenges you run into when trying to build a system this way is that now different microservices are communicating via events. So contracts on those events becomes important. How do you make sure that once one system changes the contract for their event, it's not going to break other systems that depend on those events? This is where things like the Open API spec comes into play, which has also been extended to support async APIs, so message-driven APIs as well. And to make sure that when you make a code change, you're not going to create you're not going to break other systems. That's where you can use things like Pack, which has got a proof of concept going on at the moment, which allows you to use the same toolkit that you have with Packed, but use them against the event contracts instead. So before you release your code into a production, you can run a simple command to check that the event that you're producing is backward compatible and it's not going to break the contract that you've agreed with the consumers of your events. So I love working with events, except for one case whereby I really don't like it when we try to use events as a way to orchestrate workflows within the same bounded context. And I've done this in the past myself, and I've seen other people do that as well. And you run into a few problems when you try to do that, because for starters, your workflow doesn't exist as a standalone concept anywhere in your code, anywhere you can see, apart from in your mental model of the system. And you add all these other complexities that you wouldn't have to do otherwise in terms of how you do tracing, monitoring, and logging, and so on. And the only way when you actually see the workflow is in someone's architectural diagram, and when you look at the system, you're looking at individual bits as opposed to the whole workflow and see how things are going. So instead, what you should use is in AWS is the step functions. I guess in Azure functions you have was it logic apps? That's the one, right? So that is, for me, that's a much better tool in terms of something that you should use to orchestrate workflows inside a particular bounded context. And of course, as the different functions you use as part of your step functions state machine, as those functions create state changes, you should also report them back to the Kinesis stream so that other subsystems can then also react to them and so on. So those are some high-level architectural patterns. I want to also spend some time looking at some, I guess, the implementation-level patterns, and also give us a chance to talk about, a topic that I think we should talk about more, which is how do we choose the best event source for different situations? Because besides the service themselves, we now also have additional dynamic we need to consider in terms of how does that event source interact with your functions in terms of error handling as well as concurrency as well. And the first pattern I want to talk about is decoupled invocations, which comes straight out of the SOA patterns book. So this is a very good pattern for dealing with long-running processes. With Lambda functions, for example, you have a limit on how long your function can run for. But when you have APIs using API Gateway, that limit is even shorter. API Gateway limits your integration endpoints to a 29 seconds timeout. So even though your function can run for 5 minutes, when you're using API Gateway as an event source, it will time out after 29 seconds. You also want to deal with cases whereby when you need to integrate with downstream systems that are maybe not as scalable as you are. Now you're using Lambda functions. You can scale automatically to whatever you need. But maybe you're working with downstreams that are much more constrained by, say, the database that they use, or the fact that it runs on the EC2. So scaling is not as fast and not as dynamic as you can be. So when you're dealing with downstreams that has got some potentially a hard limit on maximum throughput they can support, and when you experience a spike in traffic and you're projecting that spike in traffic directly onto your downstream, then you're going to cause the downstream to become slow and time out, and eventually that will start to be reflected in your own system as well, as if you're not handling those timeout and the errors gracefully. As the name of the pattern suggests, you are decoupling the response from the initial request. So in this case, suppose one of your users is make a post request to API to say, hey, API, do something for me. In that case, you can queue up some work for some background worker to carry on. But in the meantime, you can also respond back to the caller with 202 to say, yep, sure, we've received your request. We're going to be processing it in the background. And when the result is available, here's the location via HTTP header that you can find the response. So the caller with the location would be polling the endpoint for results as for when it's ready. But whilst the processing is still going on in the background, you will say, it's not ready yet, but when it's ready, here's you'll find the results. Until eventually the background worker finishes his job, notify the API, so the result becomes available for the caller the next time it tries to poll for results. So this allows you to amortize any spikes in traffic that you experience through the worker, so that you don't expose those spikes in traffic directly onto your downstream dependencies. So when you experience a spike in traffic, you would, based on the maximum concurrence, the maximum throughput your worker can carry out, you will amortize that so that your downstream system doesn't experience the same spike in traffic, and you would just carry on the work. Maybe take a bit longer, but you don't cause the downstream to experience an outage. At the same time, you can also, even when you have to do some expensive processing, you can still respond back to the caller a lot earlier. We can do some clever things around the UI in terms of how we communicate those status changes in the same way that when you send a message via WhatsApp, the message goes to the buffer, it gets sent to the other side, and you have different. Depending on where the state of the message, you can get different notifications in terms of whether or not it's been sent to the other side, has it been received by the other side, has it been read by the other side. You can do something similar in terms of how you communicate the status of the work that you're trying to do in the background. And by removing the urgency to give a response right away, we also give ourselves some flexibility around how we manage the failures and retries and so on. And to work for a very simple example, you've got an API gateway, and you've got a Lambda function with DynamDB as your database. And when someone makes a request to say do some work, you can save some metadata in a DynamDB table. In this case, result is no, so the result is not ready yet. In the background, I'm going to queue up some tasks with SQS. And I'm going to respond to the caller with a 202 with a location for where the result would be when it becomes available. And we have a Lambda function in the background that's polling the jobs on the SQS and it's doing this background processing. And notice that I also have a created at timestamp so that this is a way that I can use to stop the caller from polling indefinitely. So you have a way to time out the caller from polling. So when someone says, is my result ready yet? I will check the database. In this case, result is still no. So I'm sorry, result is not quite ready yet. Here's a 202, and with location of where you will find the result when it becomes available. When my background Lambda function finishes, it's going to save the result back into the database, and it's going to set the result to be something so that the next time when the caller posts again, I can say, OK, yep, the job is done. Here's a 200, and this is your actual response. So SQS is, one of the problems with SQS is that right now it's not a natively supported event source for Lambda, so you have to run your own infrastructure in terms of a cron job, for example, to poll tasks that you have in SQS. Support for SQS and Lambda is coming pretty soon, but Amazon hasn't committed to any specific dates yet. So one of the things you could consider is to use, instead of SQS, use something like Kinesis Stream or DynamoDB Stream as well, which allows you to control the concurrency that you have on the worker side of things. With DynamoDB streams and Kinesis streams, the concurrency is controlled by the number of shards you have in the stream. So you have a stream with 5 shards. Every single shard will have a dedicated instance of Lambda function so that when you want to have no more than 5 concurrent requests going to your downstream system, for example, then you can control that with the number of shards you have in the stream. And if one of the purpose of doing this is to amortize any spikes in traffic, then it also means SNS is a really poor choice here, because with SNS, every message that you publish into SNS will create an invocation of Lambda function right away. So that means, again, you're back to the land of mapping one-to-one of the traffic that you experience to the amount of concurrency that you push down to your downstream system. Another common pattern people use is PubSub. I'm sure everyone's familiar with that already, whereby you have a broker between the between the publisher of events and the subscribers that are interested in those events. In this case, for every message that you publish to the broker, it gets sent out to all of the different subscribers you have, and it's great for decoupling the different data processing you have, and allows you to segregate failure so that the individual subscribers may fail, but it doesn't necessarily have to bring down the whole thing. Again, in terms of the broker, you can use the SNS, Kinesis streams, or DynamoDB streams, and so on. And I think the default, the de facto option here would be SNS, where you can have a topic that's been subscribed by many different Lambda functions. And every time you publish a message, it's going to create invocation for each of those subscribers. And the thing you get with SNS and Lambda is that because it's an asynchronous event source for Lambda, you get 2 retries out of the box, plus the support for delta queue as well. So if you publish a message and it triggers a Lambda function, and that function errors for some reason, you get 2 retries out of the box. And if you configure a delta queue on a function, then the event that was failed, that Lambda couldn't process, will also get pushed into that delta queue automatically, which could be SQS queue, or it could be another SNS topic as well. As I mentioned, with SNS and Lambda, is 1 invocation per message per subscriber. So again, this is where we have to be conscious about the amount of traffic that we expose to our downstream system, but also the fact that with Lambda, you have a soft limit on the number of concurrent executions you have per region, which by default is 1,000, even though you could raise that with a support ticket. But again, when you're not careful, you can have have too many concurrent executions happening and end up causing all your other functions to be throttled as well. And with SNS, you can also suffer from temporal issues that you can experience. For example, if you, in a simple case where you have a very small spike in traffic and you're experiencing some errors because your downstream couldn't handle that spike in traffic, because of the retries, chances are those retries are going to kick in moments later and you'll be fine then. But if your spike in traffic is sustained for a long period of time, so then even the retries can then still fail because of the spike in traffic, and because the downstream is still under stress. And if your downstream is having a really bad day and is just suffering an outage for some prolonged period of time, then all your retries and any message that gets received and processed in that time will also just fail. So if you're concerned about, again, if you're concerned about the amount of throughput you expose to your downstream, as well as the temporal issues, then Kinesis is also a really interesting option here as a broker. With Kinesis, the retry behavior is such that if Kinesis calls your function with a batch of records and your function errors for whatever reason, then Kinesis will just keep calling your function with the same batch of records until either the data has now expired from the stream, or your function eventually is able to succeed in processing that batch. As we talked about earlier, with Kinesis and Lambda, is 1 invocation per shard, so you have a fine control over the amount of concurrency that you have at the worker layer. And the retry until success sort of mechanism allows you to have a better control, well, allows you to deal with temporal issues a lot better. For starters, we amortize any spikes in traffic with the concurrency, but if the downstream is having a problem and every single attempt to talk to the downstream is failing, then because it's retry until success, so the whole system will just keep on retrying until eventually the downstream comes back, and we just continue on from before at the maximum amount of throughput that's dictated by the number of shards we have in the stream. So we don't, when the downstream system comes back online, we don't just overwhelm it with all this traffic that's been stored and not being able to process. And besides Kinesis, you also have DynamoDB streams as well in the AWS. So a question I get asked quite often is whether or not you should use Kinesis stream or DynamoDB streams instead, and how do you choose between the two? I think the most important question to ask is, what is your source of truth in this case? For a lot of systems that we're building, the source of truth is probably going to be the database. Something gets written to the database means that it's now canon to the state of our system. Unless you're building an event source system whereby the state is not one thing, but it's the accumulation of all the events that happen that you can occasionally create snapshots on, of course. But for those kind of systems, the source of truth becomes the event stream itself, as opposed to, say, whatever snapshot you have created for the states. And there's a couple other things to consider around DynamoDB streams as well, that you're limited to, because the stream is tied to a particular table, so you're limited to the events that are, I guess, that are matched to whatever data you have in that particular table. And those events describe a domain that is DynamoDB, so items updated, items inserted, or items deleted. They don't necessarily describe what's happened in your system, which should be user created, user profile modified, profile image updated, and so on. Those are the application level events that we want to work with. But when we're working with DynamoDB streams, we have to do the mapping in our own head that, okay, a write to this particular table means users being created, and we have to work with the DynamoDB domain events instead. And from the operational side of things, there are also some interesting differences. For example, with DynamoDB, it auto-scales the number of shards in the stream, which is, on the one hand, is a good thing. It means that we don't have to implement some kind of auto-scaling mechanism ourselves for Kinesis. But on the other hand, where we want to have a fine control over the amount of concurrency that we have, now this, again, can start to impact us, because the system will automatically scale the number of shards in the stream, which means we can now, if we're using DynamoDB stream as the broker, we can now, without our control, increase the amount of throughput that we're exposing to the downstream system that we're working with. Another thing to keep in mind is that with Kinesis, you can extend the default 24 hours data retention to, I think, up to 2 weeks now. But with DynamoDB streams, you can't do that. You're limited to 24 hours of data retention. In terms of cost, Kinesis charges you based on request count as well as the number of shards, as well as shard hours. With DynamoDB streams, you only charge based on the number of pull requests you make, which, interestingly, when you process them from Lambda, those charges are free. So, which means that if you're using DynamoDB already, you kind of get the stream for free. Of course, you still pay for the read and write throughput on the table itself, but the use of the stream itself actually comes as free, which is quite interesting. So if you compare the cost of the different event sources that we've discussed today, Kinesis versus SNS versus DynamoDBs, and assuming that you're only doing 1 message per second, this is how much it's likely to cost you per month. Which, from that, you may say, well, Kinesis is really, really expensive by comparison, because it's more than order of magnitude more expensive compared to DynamoDB. But when you scale that up to, say, 1,000 messages per second, the picture now looks very, very different. Because with Kinesis, sure, you have to pay for shard hours, so even when you don't have enough throughput, you still have to pay for them. Even when no one is sending any events to Kinesis, you still have to pay for the shard. But in terms of the cost per million requests, Kinesis is much cheaper compared to the other options. So as you go to as it goes even a moderate amount of scale, SNS can be drastically more expensive compared to Kinesis. Of course, there's a lot of things that can affect how much you're actually going to pay, including the actual size of your payload and so on. So those are just estimates based on some very strict assumptions. But it still illustrates the point that when you think about the cost of the event sources that you want to work with, you have to think about the scale that you're dealing with. That can have a massive difference in terms of how much you end up paying. And you never stop there as well. You can also have a PubSub on top of PubSub. We can have your Lambda function also act as a broker to forward messages onto other systems, which allows you to have subscribers that are not necessarily supported by any of the event sources that we have. For example, SNS doesn't support S3, doesn't support a number of other downstream systems that you may want to use. You can use your own Lambda function to do the job of the broker. But when you do that, you also then take on the responsibility of dealing with partial failures. So if your Lambda function is reacting to an event that's been published into SNS, and you have to notify all these different downstream systems, what happens if one of them fails? Do you then retry everything, or do you then have to remember that only one fails so that you just keep on retrying that particular event source? So that's a particular subscriber, then you have to take on that responsibility yourself for managing exceptions and managing partial failures. And the last pattern I want to touch on is the Saga pattern, which is a pattern for managing failures in a distributed transaction, which when you have a microservices is something that we tend to run into very often when a particular user action triggers multiple API calls against different microservices. All of them then, that becomes a distributed transaction. When one of them fails, we potentially have to throw back all the state changes that we have made as already. So Katie McCaffrey, I think she's still at the Twitter. She did a really good talk at GoTo a couple of years ago on the Saga pattern itself. And one of the examples that she used was, say, a travel booking system whereby you have a transaction that involves booking a hotel, booking a flight, and booking a car rental, and so on. And what happens if you if the hotel is successful and the flight was successful and the car rental failed for whatever reason? Now you need to roll back the entire transaction and all the state changes that you've introduced so far. So with functions, you can model your actions as well as the rollback or the compensating actions as individual functions. So those are my actions. And for each one of them, I have a matching and opposite compensating action to roll back the state change. And to orchestrate that, I need to have something that can orchestrate my transaction, and that's where something like step functions or Azure logic apps can come in as the orchestrator for the transaction. Whereby I have at the start, I don't know if you can use. At the start, I have my book hotel action, and if that succeeds, then you move on to the next one to book the flight, and if it succeeds, goes to the book rental. And when everything's on a happy path, then we're just going to finish the transaction. But if at any one stage, one of these guys fails, then we go to the compensating actions for that particular book flight action. And then we also, when that finishes, we're also going to execute the cancellation for the hotel as well. And then we go to finish in the fail state for the whole transaction. So suppose I want to visit Dublin and I want to stay in the Premier Inn, then again, for my happy path, I can see that those are the functions that's been executed. But if booking hotel failed, then you execute the compensating action for the booking hotel. And similarly, when the flight booking fails, you execute the compensating action for the flight booking and then the hotel booking as well. All that code is available on GitHub, so feel free to go and play around with that. I mentioned at the start about some of the things that you have to do when you go to serverless in terms of how do you do operational side of things. I've also put a course together based on a lot of things I've learned in my time with Manning, so you can also get it from the Manning's Early Access program and get 40% off with that code. I'm also going to be talking about how do you apply the principles of chaos engineering to serverless when now we don't have service anymore. So a lot of the tools that we use for doing chaos engineering today, in terms of the chaos monkey and the Simian army of this world, they no longer apply because the infrastructure is not in our control anymore. How do we then still do resilience testing with serverless? I'm going to do that with the AWS user group here in the Oslo, I think at 5:30 tonight. And with that, that's everything I've got. Thank you guys very much for coming in so early. Fuck. For the whole time?
I don't know.
Right.
How hard is it to debug, like the system as a whole? Like with applications as a service, I guess if you got a problem, you get a stack trace.
Yep.
And here you've got all these distributed functions and bits of communication between them. How easy is it?
So even with applications as a service, when you're debugging them, you still have to rely on the tracing as you cross from one service to another. So typically, with with application as a service or even function service, you're working logically with application like a service. So you've got an API, and the chances are you have one API being an entry point. That guy have to talk to another API, and then talk to another API, and so on. So in terms of challenges, it's the same. In terms of debugging, you still need to have distributed tracing. So with Lambda, you can do the same thing as well. And that's one of the things I've done in the past, whereby is I've got middleware for my Lambda function so that when an event comes in, I inspect the event and I extract those correlation IDs, and I make sure that they're included in every single log message that I produce from the function. And when I make HTTP call or when I send a message to SNS and so on, those correlation IDs are also automatically included in those outgoing communication, so that when I publish a message to SNS, that triggers another Lambda function, and those correlation IDs will be included in the event that other function receives, and you also extract them automatically using the middleware. So that includes, for me, right now, that's not a very good set of sort of common tools they can use. I ended up having to reinvent the same tools in multiple places now, but the idea is quite similar in terms of you have middleware that does the capturing side of things, and then you have custom loggers that knows where to find those correlation IDs you have extracted, and then you have custom clients for HTTP and AWS SDK that essentially wraps around the AWS SDK itself and injects those correlation IDs, so that as a developer, I don't have to constantly think about, okay, now I need to inspect the invocation event, get the correlation IDs, include them, and make sure that I include them in every single time I log something from my function. So you still get the same sort of support from the tracing side of things, where if something happens, I can go to my log aggregation service and look for some user ID, for example. I can see all the functions that has done something for that particular user, or could be all the ID. And I also do things like sampling as well. So in production, I don't log at debug. I log at the 1% sample rate. And except for when there's an error, so if one of the function errors, then I always log the invocation event itself. So that's captured, and I can then replay that event invocation locally. So it's the same challenges as before. Nothing has really changed. The tooling has been adapted to support the new functions rather than application, but same idea. Go ahead, Shio.
So very nice, but it looks like a lot of vendor locking. Do you have any good tips how to minimize vendor locking going forward with this into the future?
So the question is that it all looks very nice, but it looks like a lot of vendor locking as well. So with the serverless framework guys, they've actually started doing this thing called event gateway. So that's potentially one way for you to get out of the vendor lock-in, whereby you have a standard set of events that can get mapped to different providers. And the serverless framework itself supports deployment to different vendors anyway. But I know vendor lock-in is a risk, but to be honest, I don't think it's a problem that many people actually have to deal with. And I have seen a lot of people, a lot of companies try to come up with solutions to this problem that they may have sometime in the future, they end up creating all this over-engineering just to compensate for that. And it's something that they end up having to pay for a very long time because you're dealing with your own custom abstractions, and you end up having to only use the least common denominator across all different providers that you may potentially want to work with. For me, I use Google BigQuery. I use different services from different providers. So ultimately, all those things are different services that you can use. So nothing really stops you from, say, using Lambda for some stuff, but other things where there's better service in Azure, for example. I think some of the AI services are a lot better in Azure than Lambda and than AWS. So I'm quite happy to have something that's also running in Azure and then use HTTP. So ultimately, different subsystems can just talk to each other via HTTP that way as well. So vendor locking is an interesting topic. I know there's a lot of people worry about that, but in practice, I haven't seen many people actually run into that particular problem. And when they have, I've yet to see an instance whereby the work you've done to prevent vendor locking actually helps you when you do end up having to deal with that. In the same way that we all use ORM for many years, worry about database migration, but when it does happen, it's still just so much work to do it anyway. So yeah, for me, it's something you should be conscious of, but maybe not necessarily try to solve until you actually have that problem. Any more questions? Okay, if not, I'm going to be... Oh, that's one more question there. So I can't really see this too much.
I was just wondering about the developer flow. So if there's a new developer coming into this project, how does it look like? I mean, to me, it's like if it's everything, like if all the code is on AWS,